finally we get to consider something very interesting in the course. This is sort of the crowning moment. It's the final chapter, and it's our reward for all of the work we've done so far. We finally get to study engines and thermodynamic cycles and cooling cycles and all sorts of interesting things where we can understand better how engines and things actually work. So we'll start off studying power cycles, and that'll be our primary focus in this chapter. A power cycle is just a thermodynamic cycle that consists of several processes so that the system ends up back where it started, but that produce power in the process of operating through one complete cycle. Now, power cycles can be broken up into a couple different categories. There are gas power cycles and there are vapor power cycles. The difference between the two is that a gas power cycle involves a working fluid that remains in the gas phase, whereas a vapor power cycle has a working fluid that goes back and forth between the liquid and the vapor phases. You might wonder, what exactly is the working fluid in your car's engine, for example? Well, that's easy if you think about it. The fact is that air comes into the engine. So does gasoline, though. So you might think, well, gasoline's the working fluid because isn't that where all the energy is? When we say working fluid, we don't mean where the chemical energy is stored. The gasoline or the diesel or however you power your car, natural gas, the energy is stored in chemical form. Technically, energy is stored in a chemical form in batteries for electric cars as well. So it's not that part that we're talking about when talking about the working fluid. And usually when you think of fluid, you think of a liquid, but when we say fluid in this class, we mean either a vapor, or I should say a gas or a liquid, either one. Both things that flow would be fluids. So what is the working fluid? What literally pushes the piston down? What applies a force through a distance? Well, it's air. You might say, well, why do I need the gasoline? Well, think about it. The air comes into the engine, and you know that more air comes in by mass than gasoline. The way you know that is probably somewhere along the way in a chemistry class that you've heard that the stoichiometric ratio is 14 or so to 1 for air versus gasoline. And remember that that's, 14 parts in terms of mass of air to 1 part of gasoline. That's, mainly air. But what is the primary component of the air? Well, let's see, you got oxygen and nitrogen, and of course there's more nitrogen in it than there is oxygen. What is it, 21% or so oxygen and 79% nitrogen? So what is it that really does the work and literally pushes the piston down in your car's engine? It's hot nitrogen. The only purpose of the gasoline, or in my case the diesel, or in someone else's case the natural gas, the only purpose of that flammable fluid is to heat up the nitrogen, is to make the nitrogen hot, give it thermal energy by converting chemical energy into thermal energy so that that nitrogen can push the piston down doing work. So the working fluid in your car's engine could be argued to be primarily hot nitrogen. That could be argued as the working fluid, and of course that nitrogen never goes into the liquid phase. So most of the time when we talk about power cycles, we're talking about a gas power cycle, but there are also, of course, vapor power cycles. If you think about the system we've looked at so far quite often of a coal-fired power plant, the coal burns, right? So there's our chemical energy, transfers heat into a boiler where water comes in, and the water is already at high pressure but then is vaporized. That way it has a very low specific volume, a very high specific volume, a low density, and as it goes through the turbine it can do a lot of work because of the principles of reversible work and how a large specific volume will typically yield a large amount of work per unit mass. And so this water has gone from the liquid phase into the vapor phase, and of course after going through the turbine and pushing the turbine blades, so it's literally steam doing work, it's steam pushing the blades, that's the working fluid therefore. When that steam is done and it exits the turbine at a lower pressure, then it goes into a condenser where it is cooled down. In fact, it liquefies so that it can go through a pump, and then that pump doesn't require a whole lot of power in order to raise the liquid water back up to the boiler pressure. So that's an example of a vapor power cycle. There are others, of course, and there are times when power cycles are used in reverse, if you will. So for pumping heat in a refrigerator, for example, or your car's air conditioner, or even your home AC unit. In that case, the working fluid, or the fluid in this case that work is being done on, is a refrigerant. that gets compressed by a compressor and ultimately expands. Of course, it goes back and forth between the vapor and liquid phases, but that's an air conditioning cycle. So we'll consider that also as we go. So we'll have primarily gas power cycles in this chapter, but we'll have at least one, the Rankine vapor power cycle, and then refrigeration cycles as well. Now, power cycles themselves can further be classified into a couple of different types. There are open power cycles and closed power cycles. Now, it seems kind of strange because you notice I've used a piston cylinder device to represent the open power cycle. Most of the time when we say an open system, what we mean is a system that can have mass flowing in and out of it. And you might say, well, that's fine because mass flows in and out of this engine. Yeah, but when the interesting stuff is happening, the valves are closed, and basically the piston cylinder device is sealed off. So really, we analyze the combustion here, the expansion stroke, all of these things are analyzed as a closed system, and you'll see that in a little bit. So despite the fact that there's actually mass flowing through it, the interesting things are analyzed as closed systems. So why is this called an open power cycle? It's called an open power cycle because ultimately the working fluid comes in and then leaves. So it's not so much the process itself and whether that process is open or closed, but whether or not the working fluid ultimately flows in and then out of the engine. Of course, that's the case here. The air that comes in your intake ultimately goes out as exhaust, having been changed somewhat. Temperature, chemical composition, and so forth. So that's why it's called an open cycle, because the working fluid enters and then leaves. A closed power cycle, like the power plant that I mentioned earlier, the coal-fired power plant, for example, in that case, the water inside of that system, the working fluid that pushes the turbine blades, remains inside of the system. So even though each of the devices, like the boiler and the turbine and the condenser and pump, are all individually open things that have mass flowing through them, in this case, the working fluid never leaves the system, or at least ideally never enters or leaves. And so it's considered a closed power cycle because the working fluid simply stays inside and just loops around continuously. So that's the distinction between an open and a closed power cycle. It's whether or not the working fluid remains in the cycle semi-permanently, I would say. Now, in real power plants, there are times when leaks develop and you've got to replace the working fluid. There are other reasons where working fluid is lost and has to be replenished. But when operating ideally, these are closed systems. It's kind of interesting also to note that the primary reason for a cycle, a power cycle, to be open is that combustion occurs internal to the system. So in the case of the engine there, you see reciprocating, the open power cycle, the air comes in, gasoline is added at some point, or diesel or something, it burns, and so the working fluid has lost its ability to do other things. It's gained, and it's not so much a lack of oxygen. There's still some oxygen available for burning more fuel, but what has happened is the temperature of the working fluid has gone up, and there's not really a good way to cool that working fluid back down without just throwing it out the tailpipe. That's the easiest way to do it. So in the example of the coal-fired power plant, you'll notice that there is a condenser, a stage, or a process where the working fluid is cooled down intentionally so that it can continue back through the cycle, whereas of course you don't take air from the exhaust, cool it back down, and then run it back to the air intake. There's no point, right? I mean, there's atmosphere all around. Let the atmosphere do the cooling. It's more efficient. So there's this distinction in what we're going to study in this chapter. So we have, of course, internal combustion typically with open power cycles, and external combustion at the boiler with closed power cycles. So finally, we get to study engines. This is fun. Except, wait a second, if you think about an engine, it's a pretty complicated thing. You might be able to recognize the engine on the left. It is, I don't know which manufacturer it is, but it's your typical, run-of-the-mill piston cylinder device. You can see the piston there, you can see the connecting rod, you can see the crankshaft in the cutaway a little bit. You can see the associated accessories on the front of the engine, the alternator is pretty obvious. Probably a power steering pump, and looks like they've even included an air conditioning compressor, and probably I mentioned the power steering pump. I'm not sure what all they've got on this. Anyway, this is an engine, and there's a lot to it, right? There's a lot of details here. Regardless of what modern engine you talk about, they're pretty complicated. In fact, there are some engines that have been developed and are no longer in use or in production that are pretty interesting we'd like to analyze. For example, the Chrysler turbine is a very interesting engine that I like. I think that if we resurrected the Chrysler turbine, we might actually be able to do a much better job with it today. This is an engine that was developed, I believe the development began in the 50s and was finally shut down in the late 60s, early 70s, somewhere in that range. But I thought it was an interesting engine. At the time, it couldn't match the performance of piston cylinder engines, which makes perfect sense because those engines had been under development for so long. And this was a brand new engine. I think Chrysler got to about the 5th generation or so, and a lot of the work centered around developing what's called the regenerator. Basically, there's a device there. We're not going to study the details of this, but there's a device that takes the hot exhaust gases, allows it to flow through, captures that heat or that thermal energy, and then reintroduces it into the working fluid that's coming in, the fresh working fluid. So at the time, they could get pretty much the same fuel economy as the typical engine of the day, which was, I think, about 17 miles per gallon, something like that. But no one really seemed to like this because the car suffered from low acceleration, low power, and all kinds of problems. It had an interesting side effect. If you really didn't care about efficiency and you weren't using the regenerator, you could still operate it, but the exhaust gases coming out the tailpipe were so hot that if somebody got on your bumper, you'd basically set their paint on fire. So it was an interesting engine, and of course the regenerator improved efficiency significantly and reduced the exhaust temperature, so it was a lot of the development. But what's interesting is there were no pistons. There were no, try to get the air and fuel in really quick and get it to burn all completely, the blink of an eye. That was not an issue because this was a turbine type engine, and so there was a compressor wheel, and there was a combustion chamber, and then essentially a couple of expansion wheels. And that combustion chamber could be sized so that once the flame began, you could just flow fuel in continuously. And that fuel would just burn once the flame had begun, would burn continuously, and you could size it so that it would have a decent amount of time to go to completion. One of the problems with engines today is you have to have a catalytic converter. What the catalytic converter does is it takes the excess fuel that didn't burn during combustion and allows it to burn. So basically the catalytic converter, it's a good thing to have. If you've ever been on a road and there's, near a classic car show and none of them had catalytic converters, you'll know why it's good to have them. You'll probably feel like you're about to die because the air is so, I don't know how to describe it. You just have to experience it, but it's not pleasant. Catalytic converters take care of the unburned fuel. But if you think about it, that represents a lack of efficiency, right? I mean, if you have to burn unburned fuel, you'd rather burn it in the engine and get something out of it. This didn't suffer from quite the same problem because you could really drive the burning of the fuel to completion if you wanted to. Another interesting thing I like about this is you could run it on all kinds of things. They ran it on old French fry oil. They ran it on, I believe they ran it on oil. I know they ran it on diesel, gasoline. They ran it on perfume. They ran it on all kinds of different things. As long as it could flow and it would burn well and not clog up the engine, it worked pretty well. And so I wonder if it could run on crude oil. Now you might think, well, that sounds horrible. I mean, I've seen cars going down the road that are old and burning oil, and they're nasty. Well, the reason they're nasty is because the oil is not completely combusted. If the oil were completely combusted, the only real significant byproducts would be carbon dioxide and water, which is what your engine produces anyway. You may not know this, but a lot of the energy in a barrel of oil is used up in refining that oil. If I remember right, the estimate is about half of the energy in the barrel is sucked away by the refining process. It may be less than that now, I don't know. I was in chemical engineering when I heard this, and I may not be remembering my facts straight, but I do know it takes a significant amount of energy to separate out the barrel of oil into its component products. So if you could burn the oil directly and completely skip the refining process, I mean, you may think burning oil is bad for the environment, but actually it would probably be good for the environment, especially if we could get complete combustion in an engine like this. And so it would be a lot cheaper, it'd be better for everyone involved. And so I wish this development of this engine had continued. Apparently the story goes that Chrysler was in financial trouble. Surprise, surprise, seems like all the big three end up there. I'm not sure if I've heard of Ford being there, but I know GM has been in trouble, Chrysler also. And my understanding of the story is that our government, as usual, even back in the 60s and 70s, put money into Chrysler, which kind of makes sense. I mean, if you think about it, taking taxpayer money and investing it in a company so that they don't go under and a lot of people lose their jobs, plus then if that company then pays back that loan with interest, well, we're getting interest on our money as far as taxpayers go. So I don't think that's such a bad deal. But anyway, apparently Chrysler was in trouble, and this was a fairly novel thing, right? This was a project that was taking up a lot of money and may not have a good payoff. It was a risky endeavor. And so one of the conditions of their loans and bailout or whatever it was, from my understanding, was that this project had to be put on the shelf and killed, essentially. And it wasn't, I don't think it was a big oil, didn't like this because, it might put the refineries out of business. I think that, it was typical day-to-day operation. Chrysler was in trouble, financial trouble, and they needed help. And if you're an investor, you don't want to invest in something that's too risky. That's just not wise. So I understand how this could come about. But the interesting thing is, at that time, they didn't have the controls that we have today. Obviously, computers were in their infancy in the 60s as far as what consumers could have. Today, the box under the hood of your car, the computer in your car, is amazing. I mean, it can do so much. And so sensor technology, controls, computer calculations and algorithms have come so far since that time. I really wish we could resurrect this engine and do more with it, because I think it holds a lot of potential, especially in the flexibility of the fuel. I mean, imagine going up to the pump and all the gasoline pumps are busy, so you just throw diesel in and it mixes in with the gasoline, you just keep going. That'd be pretty neat, I think. But looking at all these things and all that I've described, you're probably a little intimidated now, right? Because these are pretty detailed. These are pretty scary. There's a lot to them. How are we going to spend one chapter and actually understand all the details of engines? Well, the fact is we're not. What we're going to do is we're going to idealize these. We're going to approximate them. If you think about cooking a potato in the oven and you want to know how long it takes to get the potato up to 175 degrees, well, I don't know, I haven't never measured a cooking potato. I've cooked plenty of them, but I imagine you get up to 175 degrees Celsius, it'd probably be pretty much cooked. But think about it. We've already seen in heat transfer a spherical model. What if we just imagine a sphere of water instead of the potato and did our calculations, remember the transient heat transfer equations we had for a sphere, and calculate how long it would take for the center of that potato to come up to 175 degrees Celsius. That should give us a reasonable estimate for the amount of time that the potato will take to cook, because potatoes have a lot of water in them. Now, obviously, we'd get closer if we approximated the potato as a sphere that had actual properties from the potato, whatever the heat capacity of potato and etc. is, the thermal conductivity and the emissivity, not the emissivity, but the thermal diffusivity, all those properties, we could get closer and closer to a real potato. Obviously, a real potato is not a sphere, but it's not a bad start. So in the same way, what we're going to do is idealize these cycles. So even though the real cycle may have a fairly complicated shape on the PV or the TS diagram, we're going to idealize them into a series of processes that are reasonable approximations of the actual cycle processes that we can also analyze. So that's essentially what we're going to do. We're going to idealize these engines. We're going to assume away a lot of the complications. And that doesn't mean that what we'll have left is useless, right? Just like cooking a potato in the oven. If you've never cooked a potato before and you wonder, well, will it take 30 seconds in the oven? Will it take 30 minutes or 30 hours or 30 days? It'd be nice to narrow that down a little bit, right? Well, we can do the same thing here. I may not be able to predict how, your Honda Accord will compare to somebody else's, I don't know, Chevrolet Camaro. I can't compare those two engines. I don't know enough to know the details of those two engines and compare their performance, their economy, all these things. But I can tell you something that's common to both about how you could increase the efficiency of both engines in terms of a thermodynamic sense, an energy input versus output sense. So we're going to learn something here that's very important and fundamental to many of these engines.